to this video on pH calculations. We're looking again at pH calculations of strong acids and the effect of dilution. So I want to think about two different scenarios. The first one is pH changes upon dilution when we've got powers of 10 changes. So this is, for example, where we're looking at 100-fold dilution, or we're in situations here where we've got whole numbers of pH unit changes. Now these are fairly straightforward to deal with because a decrease in 1 unit of pH is equivalent to an H plus concentration change of 10 times, and each unit is the same in that way. And similarly, if we go back the other way, then if we've got an increase in 1 unit of pH, then that's the equivalent of an H plus concentration dividing by 10. So if we've got a situation here where it says a solution of HCl is diluted 100-fold, then that's the equivalent of 10 times 10. So in other words, we've got a dilution factor of 100, and so we are diluting by 10 twice, and so we're going to increase by 2 units. Question 2. One solution of nitric acid has a pH of 5, the other has a pH of 2. So we've got a difference here between pH 5 and pH 2. What is the ratio of their concentrations? So we have in one case gone, let's say we choose to go, we can write this ratio in different ways, but one way of writing it is the H plus concentration of pH 2 divided by the concentration of H plus at pH 5. So saying what factor increase is there from going from 5 to 2? Well, we check it's 3 pH units, 1, 2, 3. So that means each one is times by 10, so times 10 again is times 100, times 10 again is times 1,000. We'll just check we've got the fraction the right way up. Yep, pH 2 should have a higher concentration of H plus than pH 5, so it should be 1,000. Now you're very welcome to write the ratio in the typical way. pH 2 to pH 5 of 1,000 to 1, like this. But quite commonly in physical science, instead of writing a ratio like this, you just do one number divided by the other in order to get it. So those are two ways of writing the same thing. Now, if we've got pH changes that we're trying to work out when we have other factor dilution, so non-powers of 10, then the basic strategy here is going to be to try to turn pH into the concentration of H plus ions using the formula on the right hand side, or we might have to work out pH using this formula on the left hand side, and we're still using, because this is strong acids, we're going to use the initial concentration of acid is equal to the H plus concentration at equilibrium for strong acids. So let's see how that works out in practice. So we've got a 25 centimeter cube solution of this concentration of hydrogen iodide or hydroiodic acid, and we're diluting it with water to a total volume of 50 centimeters cubed. So we want here to try to work out our sort of basic strategy is going to be that we've got the pH over here. We want to go via the H plus concentration because we know we can use this formula up here to get there. We want to try and work out the H plus concentration. And so in order to do that, we're going to start with the number of moles of H plus ions, which we can get from the information in the question. This is the volume and the concentration. And then if we just do concentration is number of moles divided by volume, we can get the H plus concentration. So let's sort of work that through. Number of moles of H plus ions is the same as the number of moles of acid in the original sample, because of our assumption, And so if we're going to do concentration times volume on that, then we've got concentration of 0.5 and the volume is 25 times 10 to the minus 3 to turn it into moles. And that is going to give us 0.0125 moles. So if we then try and work out the concentration of H+, we just need to do moles divided by the total volume now, which is 0.0125 divided by now the total volume, which has gone up to 50 centimeters cubed. And when we do that, we're going to get a concentration of 0.25 moles per decimeter cubed, which hopefully makes some sense. We've had 25 centimeters cubed diluted to 50, so we've diluted it 2 times. We're expecting that concentration to halve. And final step, we just do our pH is minus log base 10 of that number, and we should get a value of 0.60 to 2dp. Okay, final one, question 4. Solution of this time is hydrobromic acid, pH 3.5. It's diluted to get this pH, 4.98. How many times was it diluted? And the key here is that we want to try to turn our pH into H+ ion concentrations. Might be worth pausing the video, see if you can do it. Here we go. So we're going to turn pH into H+ ion concentrations for each one. So I'm just going to actually write them up here just so that we can see. So this one would be concentration of H+ equals 10 to the minus 3.5. No problem with writing it like that. And then this solution here has got an H+ ion concentration of 10 to the minus 4.98. I'm just going to give these some subscripts just to see. So this is a lower pH than this one. So in increasing pH, that must mean we've decreased the concentration of H+ ions. And therefore this one must be the original. So I'm just going to call that O. And this one is the diluted one, so I'm going to call it diluted. Now if we want to work out how many times it's been diluted, then we need to do the original concentration divided by the diluted one. So we're going to write concentration of H+ original divided by concentration of H+ diluted. And so if we work that through, 10 to the minus 3.5 over 10 to the minus 4.95, we should get a value that when we work it through comes out to be 30 in our calculations. So we've diluted it 30 times. Now it's really important in these calculations that we turn our pH into H+. Don't try and combine pHs. Really important. Because pH is a logarithmic quantity, it's incredibly difficult to combine it without making mistakes unless you're really confident in your rules of logs. You're much better turning it into concentrations of H+, and in some cases, number of moles of H+.